Let's use derivative rules to find the rate of change of a logistic function. The example I'll try this on is 8 over 1 plus 2 to the negative x. Now if we want to find the first derivative of that, we may need to know several derivative rules. One would be quotient rule. That's where we're trying to take the derivative of a fraction of functions, and we can do f prime g minus g prime f over g squared. That's an option. Another option would be to use product rule, where you could rewrite the thing as 8 times 1 plus 2 to the negative x to the negative 1. It is an option. And product rule says f prime g plus g prime f. I think I'm going to go with the quotient rule approach here. So let's rewrite it as 8 prime times 1 plus 2 to the negative x minus the derivative of 1 plus 2 to the negative x times 8. And then divide by the denominator squared. Okay. So since the derivative of a constant is 0, this term will actually go away. But we're going to have to take the derivative of 1 plus 2 to the negative x. The 1 is just a constant. That'll end up going away as well. But what is the derivative of 2 to the negative x? There's a rule for that. Derivative of a constant to the power of x. So if we have some constant b raised to a power of x, and we want to take the derivative of that, it's similar to e to the x, except it will be b to the x ln b. Now the thing that makes this just a little bit tougher here is we don't even have b to the x, we have b to the negative x. So we should do a chain rule here. If we were trying to do 2 to the x, for example, it would have been just 2 to the x ln 2. But we're trying to do 2 to the negative x. So let's let g equal negative x. That would mean we're trying to find the derivative of 2 to the g, which would be, according to the formula above, 2 to the g times the ln of 2, but because it's chain rule, times g prime. So, after rewriting it, we'll get 2 to the negative x ln 2 times the derivative of the g, which is just simply a negative 1. Okay, so that's what needs to go in our numerator. Two to the negative x times ln 2 times negative 1 and times 8 over 1 plus 2 to the negative x squared. So our negatives here will cancel. And it looks like we'll get 8ln2 times 2 to the negative x over 1 plus 2 to the negative x squared. Okay, now just to see if that makes sense, that derivative, let's plug it into a graphing program and just verify that that really could be the derivative of this logistic function. So I'll bring up the Desmos program here. It's just a web app, desmos.com. We can type in the original function. Okay, there's our logistic function. Now let's type in the derivative and see if it makes sense. Okay. Yeah, so one of the things we're looking for with the logistic function's derivative is we want it to have its maximum value when the logistic function is increasing most rapidly. So the logistic function increases most rapidly at the inflection point. As you can see, that's where it's steepest. And so it should make sense that the derivative of the thing should have its highest value at x equals 0. So that lines up pretty well. One of the other things we'd be looking for is we want the logistic function slope here to decay as x increases from 0. So the slope is getting smaller and smaller, the rate of the change is getting smaller. And so yeah, we want to see our derivative value head towards 0, which means that the slope is getting less and less steep, both to the right side and to the left side of 0. When it first starts off, it should have a very gradual slope, so we want a very low derivative value there. And yeah, I think it looks pretty good. Okay, so can we do this generally then for any logistic function of the form L over 1 plus AB to the negative x? All right. We'll just try the quotient rule once again here. We'll get L's derivative times 1 plus AB to the negative x plus, minus 1 plus AB to the negative x's derivative times L 1 plus AB negative x squared. Okay, once again, this will go away. The 1 will not be needed. We just need the derivative of AB to the negative x. So that's going to be itself times the natural log of the base times the derivative of the exponent. And then we'll have that L at the end. And we'll have 1 plus AB to the negative x squared down here. Okay, so if we simplify it, looks like LAB to the negative x times the natural log of b over 1 plus ab to the negative x squared. Great. Okay, so one more. Can we find the derivative of the general logistic function when we have L over 1 plus AE to the negative kx? That one's going to be tricky. Let's see. I'll do quotient rule yet again. We'll have L prime 1 plus AE to the negative kx minus 1 plus AE to the negative kx prime times L divide by 1 plus AE to the negative kx squared. Okay, just like the others, this part is going to disappear, so will the 1. And we need the derivative of AE to the negative kx. So that's going to be itself. But this is a chain rule because of the k and the negative. So we'll want to take the derivative of the exponent, which would be negative k. We'll leave the L there. Okay. And then we'll divide by 1. Oh, there's a negative out front too. 1 plus AE to the negative kx squared. And we could just cancel these negatives. And looks like we got L A K e to the negative kx divided by 1 plus AE to the negative kx squared.